Tonight on Nova, is Antarctica melting? A mountain of ice is on the move, and its fate could spell disaster.
It does matter to everybody in the world what that ice sheet is doing.
Are we on the verge of the next ice age? Or a great flood that may consume the world's coastlines? The race for answers sparks a Nova expedition to the ends of the Earth. Warnings from the ice.
The bottom of the world is a beautiful but unforgiving place. An entire continent cloaked in ice. Antarctica. Just over 700 miles from South America. Yet it's so isolated. Its existence was a myth until the 19th century. For over 20 million years, Antarctica has been the coldest place on Earth. But recently, things have been heating up. In 1995, an iceberg the size of Rhode Island broke off from the Larsen Ice Shelf along the Antarctic coast. And a large portion of the ice shelf disintegrated in a matter of days. Over the last half-century, the coastal ice on the Antarctic Peninsula has been gradually disappearing. What does it mean? Is Antarctica melting? What would happen if all this ice were unleashed into the oceans?
Inbound! Straight out from the gates!
Kevin Costner's epic film Waterworld depicts Hollywood's version of the disaster. A future where dry earth is rare and precious.
Jerks!
Beneath the waves, civilization lies destroyed, drowned by melted polar ice caps. Is this a science fiction fantasy, or could Waterworld really happen? To find out, scientists are heading south to Antarctica. Their first stop is New Zealand, where they gear up to battle the elements. Then it's an 8-hour flight in a military cargo plane. The LC-130 Hercules, affectionately known as the Herc, is not designed for comfort. But it's one of the few planes tough enough to do the job. Every summer, Hercs deliver hundreds of scientists to Antarctica. They have just a few short weeks to unload supplies, set up camp, and collect crucial data before the dark polar winter sets in. These are the ice experts. They're on a mission to unlock the secrets of Antarctic ice. Is it melting? Is it moving? Most importantly, how will it affect the rest of the world? Taking the pulse of Antarctica is a daunting task. The continent is 1.5 times the size of the US and is covered with 7 million cubic miles of ice. The giant ice sheet in the east is probably more than 15 million years old. But the West Antarctic ice sheet is younger, and scientists fear much less stable. While the ice on the eastern side of the continent rests on dry land, most of the West Antarctic ice sheet sits precariously on bedrock that lies below sea level. Part of the ice sheet is in direct contact with seawater, which is much warmer than the air. And that means the ice can melt much faster. The West Antarctic ice sheet is as big as Mexico. If it broke up and fell into the ocean, sea level would rise by almost 20 feet. That's enough to redraw the world's coastlines, flooding Bangladesh and Florida, London and New Orleans. The deluge would wipe out entire cities and render millions of people homeless. Many experts believe the West Antarctic ice sheet is doomed to collapse. The question is, how long will it take? 2,000 years or a few decades? The answer may lie in the nature of the ice itself. The ice sheet is made up of layers of snow that piled higher and higher over the millennia and then compacted under their own weight into ice. In some areas, the ice sheet is almost 3 miles deep. And when ice gets this thick, it can't sit still. Antarctic ice is constantly on the move. When the ice sheet reaches the mountains, it squeezes through the ridges, forming valley glaciers. Across the continent, scientists are trying to track the movements of the ice. On the eastern side, one research team is probing the depths of the Meserve Glacier. A year ago, chainsaws carved this 200-foot tunnel into the heart of the ice.
A tunnel provides one with a spatial picture that you can look at the geometry of these features in a way that's unique. You can't do it any other way.
Charles Raymond is trying to understand how ice moves.
We put these bolts in vertical lines about a year ago, and we lined those lines up so that these figures were actually squares. And what's happened in the meantime over the intervening year is that the top up there has moved this way, and this down here has stayed relatively fixed in place. And so there's been this kind of motion, which we call shearing, that deformed these lines into inclined lines from vertical to inclined, and the little squares are now parallelograms.
The bolts reveal that the ice at the bottom of the glacier only moved about 1/5 of an inch in the last year. But the ice above it flowed much faster. The top of the Meserve Glacier moved about 6 feet.
What we have to remember first is that the ice moves. It flows. And if you think about taking pancake batter and pouring it onto a plate, it will spread. Gravity pulls it down, it slumps out, and so it flows. Ice does exactly the same thing. It snows on top of the glacier, the weight of the ice pushes it down, and it spreads out, and so you have moving ice.
The ice in Antarctica is so thick, gravity forces it to spread out towards its edges. Eventually, there's only one place for the ice sheet to go: into the sea. As it pushes off the coast, the ice thins out and begins to float. It is now called an ice shelf. Above the water, the ice shelves look like towering cliffs, but they are actually just the tops of enormous floating ledges of ice that extend hundreds of feet beneath the surface. As the shelves break apart, colossal icebergs are launched into the southern oceans. Antarctic icebergs are famous for their extraordinary size, often several miles long. Floating among the majestic icebergs is a less glamorous type of ice, but one that's extremely important for Antarctic wildlife. Sea ice forms when ocean water freezes. Just a few feet thick, sea ice is the perfect platform for marine mammals like seals, and for birds, especially penguins. In the water, penguins hunt for krill, fish, and squid. But they mate and breed on land or on the shifting sea ice itself. During the winter, as air temperatures drop, the sea ice freezes into sheets and expands outward from the coast. This image, produced by microwaves, shows how sea ice grows and shrinks with the seasons. At the height of winter, the thin veneer of ice stretches almost 1,000 miles across the ocean, in effect, doubling the size of the continent. Sea ice protected Antarctica from human invasion for thousands of years. When sailors finally did venture south, the floating ice tormented them. In 1914, the British ship Endurance headed for Antarctica. Explorer Ernest Shackleton was hoping to march across the entire continent, but he never made it ashore. Sea ice closed in around the Endurance and carried it in an aimless drift for 9 months. Documenting their ordeal with a film camera, the crew struggled to cut the boat free, but failed. Finally, they were forced to abandon ship and could only watch helplessly as the mighty Endurance was broken and crushed by the shifting ice. Civilization was more than 1,000 miles away, and Shackleton was left with just 3 small lifeboats. He spent nearly a year battling crushing ice floes and hurricane seas, but overcame the odds. With one of the boats, he was able to reach a small whaling station in the South Atlantic. 2 years after they'd set out, the crew of the Endurance was rescued. Amazingly, all 28 men survived. Antarctic exploration has come a long way in the last 85 years. Today, 13,000-ton steel-hulled icebreakers slice their way to the coast. One of the early camps has exploded into a scientific boomtown. McMurdo Station is headquarters for the U.S. Antarctic Program, supported by the National Science Foundation. Hundreds of scientists are based here. Many of them study the crucial relationship between ice and climate. In the last century, global temperatures have risen about 1 degree Fahrenheit, possibly as a result of industrial activity. But on the Antarctic Peninsula, it's warmed up more than 4 degrees during the same period. Here, large chunks of the floating ice shelf are breaking away. And native plants are thriving along the rocky coast. Scientists do not blame global warming for the massive meltdown. Instead, they believe it's part of a natural, local climate shift. Looking back in time, it's clear that climate has undergone some major changes with direct impact on the size of the ice sheets.
In the last million years, the glaciers have grown and shrunk about 10 times, and they typically spend about 90,000 years growing and 10,000 years melting, and 90,000 years growing and 10,000 years melting, and so on.
Ice ages, each lasting 100,000 years, have come and gone again and again. At the height of the last ice age, 21,000 years ago, much of North America was frozen under a giant ice sheet. And temperatures were about 20 degrees colder than they are now. Today, we are in one of the shorter warm periods between the ice ages, called interglacials, when much of the ice melts. As it melts, more and more water flows into the oceans, and sea level goes up.
Sea level is ultimately controlled by how much water is in the ocean and by how hot that water is. If we take water out of the ocean and put it in an ice sheet, then the ocean gets lower. If we take water out of the ice sheet and put it back in the ocean, sea level comes up.
During the ice ages, water accumulated in the expanding ice sheets, and global sea level went down. But for the last 20,000 years, the ice has been melting, and the oceans are getting bigger.
Over the last 20,000 years, sea level has been rising. Over the last 4,000 years, it's been rising about 2 millimeters a year. And so the concern is whether that rate is going to continue, or whether it's going to accelerate, or whether it might even decelerate.
So far, the collapsing ice shelves haven't raised sea level at all, because they were already floating and displacing water long before they broke up. For sea level to rise significantly, ice from a grounded ice sheet has to flow rapidly into the sea. And that's most likely to happen in West Antarctica, where the ice sits on bedrock below sea level. To find out how vulnerable this ice sheet is, scientists like Bob Binshadler are heading out into the Antarctic wilderness.
We're out there trying to understand how the ice sheet works. What are the forces that make the ice move? And if those forces change, how is the ice sheet going to respond to those changes?
But tracking the West Antarctic ice sheet isn't easy. Even during the summer months, conditions can be brutal. The team's only protection is an insulated box that serves as a traveling base camp. It's a kitchen, lab, and dormitory squeezed into a 10-foot by 10-foot room. When the winds die down, team members set out in pairs across the surface of the ice. Their mission is to locate and map hundreds of marker poles spread out across 4,000 square miles of the West Antarctic ice sheet.
We use global positioning satellite receivers, which tell us our precise location. So we go to a site and we put the receiver antenna on top of the pole, measure its position, and then come back a year later and remeasure its position, and then that tells us how far it's moved in that year.
Pole by pole and day after day, the team collects the data. Every few days, base camp moves on, and the process repeats itself until something breaks down. With the wind chill plunging to 50 below, equipment repair is a challenge.
Fixing the skidoo in the cold is really difficult. One of the problems is that your tools have been outside, probably, so they're very cold. So you're not going to be able to work with bare hands, fingers. So trying to put a socket on a nut can be difficult. Maneuvering some of the tools in tight spaces can be difficult. And you'll drop things. You'll drop things and it'll go into the snow and you won't be able to find it, and you'll just be fishing around for half an hour just trying to find the nut that just fell. So those kinds of frustrations just limit your ability to move and do the things that you're accustomed to being able to do.
As they make their daily rounds, the scientists face more than frustration and cold. The movement of the ice sheet can open up gaping cracks called crevasses. Crevasses can be 50 feet wide and more than 100 feet deep. Worst of all, sometimes they're invisible, covered by fragile bridges formed by blowing snow. Walking along the surface, a researcher would never see the giant chasms until it's too late. This was a demonstration, but Bob Binshadler knows firsthand the terror of an unexpected plunge.
It's just like having a rug pulled out from underneath you. You're walking on something that you think is a firm surface, and all of a sudden it disappears, and you just shoot downward.
Bob must be all the more vigilant because he spends much of his time driving a heavy skidoo across the ice.
The skidoo makes it even more hazardous because you have something that is about 5 times your weight, and if the two of you fall into a hole, you don't want to be anywhere close to that machine.
Over the years, crevasses have killed several explorers and scientists. In this case, the driver survived, but his bulldozer is lost forever. The data that Bob's team is collecting may help to explain why parts of the ice sheet are riddled with crevasses. Measurements reveal that some of the poles have moved almost half a mile in a single year. They are riding on a 200-mile-long ribbon of rapidly flowing ice called an ice stream.
The ice stream is probably best described as just a river of ice contained within the ice sheet. Ice sheets in general are thought to be very slow-moving features, slow-moving just meaning just a few feet per year. But these ice streams, these faster rivers, rapid currents, will go about a few hundred meters per year, up to 700 meters per year in the case of the ice streams that we're studying.
The ice streams move so fast, friction at the sides splits open the ice, creating enormous crevasse fields. The ice streams are so large, their true size and shape can only be appreciated from space. Satellite imagery of West Antarctica reveals several areas where rapid movement has occurred. Through these ice streams, highlighted in blue, ice is flowing from the heart of the West Antarctic Ice Sheet out into the huge floating Ross Ice Shelf.
Ice streams are 50 to 100 kilometers wide, about a kilometer thick. They go 10 to 100 times faster than the interior ice. So they're capable of moving vast amounts of material into the oceans.
But why are the ice streams moving so fast? Geologist Don Blankenship believes the answers lie beneath the ice, in the rocks that support it.
The problem of understanding the dynamics of the West Antarctic Ice Sheet in the context of the geology is that the geology is largely unknown. It's covered with ice. If something sticks up through the ice to study, to get a piece of, to get a rock, it's probably an anomaly. It's not telling us what's really going on. What's really going on is a secret.
To see the rocks beneath the ice, Don Blankenship would need X-ray vision. Thanks to this airplane, he has it. This twin otter is scanning the ice sheet with a slew of high-tech remote sensors, including radar that can see right through the ice.
The ice-penetrating radar gives us the bed. The laser altimeter gives us the nuances of the surface to within a fraction of a meter.
56849, SIG is 4.6.
And there are instruments that measure the magnetism of the rocks, as well as the gravitational pull of the Earth.
The radar will be in 20 nanoseconds, 250 millivolts range.
With the aircraft, we can fly around and get at least indirect indications of where the rocks are dense, where the volcanic rocks are, where the faults are, all kinds of things that we can put together to understand the geology.
Flying over the ice sheet, the sensors detected rocks that were less dense, a characteristic of sedimentary layers which form at the bottom of oceans.
Okay, start of segment.
Okay, so this is
In another experiment, sound waves revealed evidence of a layer of soft, wet mud directly below the ice streams.
probably a good place.
Don believed that this mud was making the ice streams flow so fast.
Went to the site that we selected.
But to prove this idea would take a more direct approach.
Our approach is to get access to the base where the action is, where we believe the action is. And we do that by drilling.
1, 2, 3.
Barclay Cam is part of a team that's drilling a hole straight down through an ice stream to take samples from the bed below. If there's mud down there, he's going to find it.
The normal methods of drilling, it takes a year or so to drill a hole deep enough to serve the purpose. We have to do it to get an appreciable amount of information. We have to do it much faster than that.
Okay, we're ready.
So we have a hot water jet that melts its way rapidly down into the ice.
Finding water to supply the jet was no problem, but producing and maintaining enough heat was a bigger challenge. To do the job, the team converted 8 car wash heaters into industrial-strength ice melters.
The temperature of the ice is minus 25 degrees centigrade, and the air temperature is always below freezing.
Airborne, 4 systems.
The near boiling water is pumped through almost a mile of rubber hose and pressurized to 1,500 pounds per square inch. The resulting jet easily cuts through the rock-hard ice.
Okay, Airborne, shut it off.
The biggest single challenge of the cold to our operation is the hazard that some part of this system will freeze up, or all of it will freeze up.
To avoid freezing, the drill must operate continuously until it reaches the bottom, more than half a mile down.
Okay, it's ready to go down now.
We can drill a hole at roughly 3,000 feet deep within a time less than a day. And then we can get to the bottom and then put down instruments that will reveal something about what goes on down there.
just as Don Blankenship had predicted, the team found mud directly under the ice stream. When they pulled up their probe, it was coated with a thick, gooey mixture of wet clay, sand, and pebbles. Under the microscope, they found these diatoms, the tiny fossils of prehistoric algae. Together, the evidence points to one conclusion. Where there is now an ice sheet, there once was an ocean.
One thing we all agree on is that the West Antarctic Ice Sheet does disappear during the interglacial periods, which happen about every 100,000 years. It may not disappear in this one, the current one that we're in, but it does disappear. The question that's really important is what triggers the disappearance?
The ice streams are key to solving the puzzle. By carrying large amounts of ice quickly into the sea, they are gradually eating away at the ice sheet. But what's driving the ice streams forward? Is it just the underlying mud? Barclay Cam's drill turned up some intriguing evidence that something else might be going on. A half a mile down, he found signs of a very thin layer of water, possibly less than a millimeter thick, flowing between the mud and the ice.
We learned there that the base of the ice is at the melting point. And we learned that the pressure of water at the base of the ice is very high. It's almost high enough to float the glacier off its bed. And that is a physical driving a phenomenon which allows the rapid motion, this near flotation of the ice.
But where is the water coming from? Why is the base of the ice melting?
Got our high tension coming up. Port Ashtec and TCG are up.
While flying over the ice sheet, Don Blankenship's sensors picked up evidence of magnetic rock and a cone-shaped mountain beneath the ice.
And looks good, we're reading 59846.
At the surface, there was a round depression 4 miles wide.
Ice flows downhill, and whenever you have a depression, that means that ice on one side is flowing in, and ice on the other side is flowing in, and it has to go someplace. Mass is conserved. And so what turns out that the only way for that mass to go someplace is to be melting away at the bottom, for that ice to be flowing into essentially a depression on the bottom that's formed by very high heat flow.
It was an active volcano melting the bottom of the ice. Even a volcano isn't enough to destroy an entire ice sheet, but it is evidence of some major geological activity. Don made his discovery just west of the Trans-Antarctic Mountains. Here, 2 continental plates have moved apart. In the middle, the Earth's crust is very thin, allowing heat to flow up from below. This could be contributing water to the base of the ice streams. But scientists worry there could be an additional source of heat.
We have these fast-moving ice streams, which are lubricated on the bed, and between them are ridges of slow-moving ice, which are probably frozen to their beds. The temperature at the bed depends on a number of things. It depends on how hot the Earth is underneath and how much heat comes up, but it also depends on how hot the atmosphere is.
The atmosphere above the ice sheet is extremely cold. But during the last ice age, it was even colder.
The bed doesn't notice immediately when the temperature at the surface changes. In the same way that if you take the Thanksgiving turkey out of the freezer and put it in the oven, the center of the turkey takes a while to notice that it's in the oven. It remains frozen for a while. When the air warmed at the end of the last ice age, the bed of the glacier is just now realizing that. It takes that long for the heat to get down. So there is some concern that the warming at the end of the last ice age would now be causing melting at the bottom, and that as more melts, it goes faster. That makes friction, which makes heat, which melts more, which goes faster, and same thing, disaster.
If the ice streams are speeding up, disaster could come sooner rather than later. But it's hard for scientists to identify any long-term trends when they've been tracking the icy rivers for such a short time. To forecast the future of the ice sheet, they'll need a better picture of the past. Kendrick Taylor is one of the detectives trying to decipher the climate history of Antarctica. He's looking for clues embedded in the ice itself.
When I look out here across this surface here, I see, of course, a small portion of the West Antarctic Ice Sheet. This is really just a small, little teeny portion of it. But I know that underneath there, there's just a series of layers stacked up one on top of each other. And those layers contain a record of what the climate has been in the past.
The layers are obvious just beneath the surface.
This is the surface of the snow right up here. This is a winter sequence. This dense, darker snow up here, that's snow that fell last winter. This very light layer, it's a surface hoarfrost layer which formed last summer when it was warm out. This is a dense layer here, another winter layer sequence in here, and then this is a summer sequence right in here. Now what's really interesting about this is just by looking at this I can tell you certain things about what the weather used to be like here. First off, this winter it snowed a lot more than this winter it did. You can tell that simply because it's thicker. And during this summer was particularly warm. You can tell that because of this ice layer right in there. That happens when the snow gets very warm. It gets kind of slushy, and that surface layer refreezes and forms a very hard ice crust. What's going to happen here is more snow is going to fall on the surface, and this whole sequence here is going to get compacted and compacted down until it becomes solid ice.
Ken's job is to retrieve the compacted layers in an ice core. Each meter-long cylinder of ice represents about 10 to 20 years of snowfall.
And this ice core is going to give us a window on what's happened in the past. By looking at this ice, we're going to be able to pull up ice that's over 100,000 years old. We can make measurements on that ice. We can determine what the climate has been for 100,000 years, and we can determine the general nature of this ice sheet during that 100,000 year period. So for some of the ice cores, we have to be very careful about how we collect them.
Number 9.
We have to wear special suits and handle them very carefully to make sure that we don't contaminate the core in the process of working with it.
All right.
Scientists have been collecting ice cores for decades. But small rigs like this one can only drill about 450 feet. The ice at that level is only about 1,800 years old. At this site, the really old ice is more than a half-mile down. Reaching those depths requires a very long drill. This is the biggest ice core drill rig in the world. Ken's team will use it to drill through Sipel Dome, a ridge of ice that rises up between two ice streams. The ice core they collect will provide important clues about the history of the West Antarctic Ice Sheet. That is, if they can get the drill to work. Greg Lamori is one of the managers on the project.
We broke one of the couplings that connects the shaft to the inner core barrel that does the actual drilling. They don't have this particular coupling in McMurdo. They're able to machine it up for us in a couple of hours because it's not a very hard part to make, and have a very good machine shop there. But now we're really waiting on the weather. And around here, the weather can sock you in for over a week sometimes, and they just can't get the Herc flights in. And so until we can get that part in off the Herc, we're kind of held up.
For the crew at Sipel Dome, sitting out a summer blizzard is frustrating but not life-threatening. More than 50 people live here at one time, and they have shelter, heat, and food to weather the storm. But this wasn't always the case. Frozen in time by the dry Antarctic air, the supply hut of Robert Falcon Scott has sat undisturbed for almost a century. A British naval officer, Scott led 2 high-profile expeditions to the frozen continent. In 1911, he set out for the holy grail of Antarctic exploration, the South Pole. The journey would take him across almost 1,000 miles of icy terrain, deep into the heart of the continent. He rejected the use of sled dogs to haul provisions, instead relying on Manchurian ponies. They were soon hobbled by the extreme cold, and Scott and his 4 companions were left to drag their supplies on foot. After 10 weeks of exhausting labor, they arrived at the pole, where they found an empty tent. A Norwegian team had beaten them by 1 month. Scott recorded his feelings in a diary.
It is a terrible disappointment, and I am very sorry for my loyal companions. It will be a wearisome return. Great God, this is an awful place.
Malnourished and depressed, the British headed for home, but they never made it. A relentless windstorm stopped Scott in his tracks, just 11 miles from a supply depot.
We shall stick it out to the end. But we are getting weaker, of course. It seems a pity, but I do not think I can write more.
8 months later, rescuers found Scott and his companions frozen in their sleeping bags. They covered the site with a monument of snow, and Scott's tent became his grave. Today, visitors are better prepared for the unforgiving Antarctic weather.
When we're out here in Antarctica, it can be relatively benign weather sometimes, and then sometimes it can get violently, it can change pretty violently for the worse in a relatively short period of time. We had a scientist...
Steve Dunbar teaches scientists how to survive the worst Antarctica has to offer, including winds that can reach 100 miles an hour and winter temperatures that plunge to more than 70 below zero.
I was out here one time doing a search and rescue exercise with some people, and the weather ended up closing in. I watched it from about 3 miles away. There's a good landmark, and I watched it come in, and in less than 2 minutes, we had less than 20-foot visibility. You darn well better get a camp up and get out of the elements, or you're not going to last very long out in this sort of weather. The shelter is probably the most important thing that you need to do, and you need to get that up first. Once again, break it free and carefully lift it out.
Most scientists come in the summer, but even then, they face the threat of sudden storms.
Calories are gold, and all the calories that you have on board, all that food that you've eaten, all the fats that you have stored, you only have so many of them. And when you run into a situation here where you find yourself stressed by the weather or stressed by the environment, you need to go ahead and hang on to all those calories and spend them wisely. So you want to go ahead and build your snow shelter as quickly and as efficiently as possible.
Stronger than any tent, the best protection from the biting winds is a shelter made from blocks of snow.
And it's really dramatic. The second you get into your shelter, you just feel that much warmer.
Safety is always an issue in Antarctica, especially in the isolated research camps like Seipel Dome, where Ken Taylor's team has been waiting patiently for a replacement part for the big drill. Finally, the weather has cleared, and the new coupling is flown in from McMurdo, almost 600 miles away.
This one, the bigger one.
With time running out on their work season, the crew has only drilled about 25 feet, with 3,000 more to go. In all, it will take 3 or 4 summers to reach the bottom. The drillers are weathered veterans of ice sheet research. Before coming to Antarctica, many of them investigated the ice on the opposite side of the planet, in Greenland. Like Antarctica, much of Greenland is covered with an enormous ice cap, the last of the great northern ice sheets. The ice is over 2 miles deep, and the bottom is made from snow that fell about 250,000 years ago. American and European teams collected ice cores here that have revolutionized our vision of climate. The ice cores were sliced up, and every aspect was scrutinized in detail, from their crystalline structure to chemical content and electrical conductivity. In this test, 2 electrodes are dragged across a clean surface of the ice core. The readout reveals fluctuations in atmospheric dust content. A dip on the graph indicates more dust and a drier, colder climate. Climate experts used to believe that the warm-up after the last ice age was slow and steady. But the Greenland ice cores told a very different story. Instead of gradual warming occurring over thousands of years, the end of the ice age 11,000 years ago came suddenly and swiftly.
When you look at the long record, the warm-up from the ice age to today was not a smooth process. It jumped. You'd be coming along, and then, boing, the world changed. And the boing may have taken 50 years, it may have taken 20 years, some of the boings 1 to 3 years. And the change is something 1/3 to 1/2 of the whole warming from the ice age. Just the world changed.
Looking back in time, the last 10,000 years have been marked by dramatic changes. Century-long cold spells and decades of drought. But these were nothing compared to what came before, when average yearly temperatures fluctuated wildly, creating climate shifts within a human lifetime that are nearly unimaginable.
If we remember the Dust Bowl, it got dry and the fields blew away and the crops died and people starved or they moved. The Dust Bowl was a change in the weather, a change in the climate that would be barely a blip in the climate records we're seeing. So if you think of the impact of the Dust Bowl on the people living in Oklahoma when that happened, that was a small change. That was not a big change.
This is the crucial distinction between climate and weather. The natural disasters we've known, including hurricanes, tornadoes, and floods, are weather events taking place in a climate that is basically stable and predictable. But if the climate changed, if the average temperature suddenly went up or down by even a few degrees, it could radically disrupt life as we know it.
One way to think of these large changes in climates is as if the climate that you find up in the Midwest in Iowa or something like that was suddenly occurring down in Texas.
The cause of such rapid shifts is a mystery. But some scientists fear there are critical thresholds in our climate that once crossed could trigger the sudden change.
What it means is that there may be sort of triggers or thresholds in the climate system so that you can be in this one climate state and you can be changing something, perhaps greenhouse gases, perhaps other aspects of the climate system, and you won't see any change or very much change in climate. And then once you cross a critical threshold, or you sort of trip a trigger, if you will, the climate abruptly changes to another state, and it catches you by surprise. So you can be sort of monitoring climate, and you can be saying, well, there's nothing going on, there's no real changes, we don't have anything to worry about. And then all of a sudden, boom, you've got a problem, and it's there, and it's sort of too late to do anything about it.
When it comes to global warming, popular fears usually focus on the water world disaster, melting polar ice caps and devastating floods. But now there's concern that if the world gets too warm, high temperatures could help trip a climate trigger and plunge us into a colder and icier age. If the ice teaches anything, it's that there is no room for complacency. This is a volatile world. If climate shifted abruptly in the past, not just once, but repeatedly, it's inevitable it will happen again. The question is, when?
Ultimately, we would like to know what faces us in the future. Will the climate do this again? Should we get ready for it? Will our actions affect it? If we humans do this, will the climate change? Can we change it so that it's nice to us, or might we change it so it's very bad for us?
The ice core at Sipel Dome is one piece in a giant puzzle. If researchers can date the ice at the bottom, they may find out when the West Antarctic Ice Sheet last collapsed. And the ice core itself could help solve the mystery of rapid climate change. Slowly, the ice is surrendering its secrets. Here in Antarctica, they're hoping it will answer some important questions about our future before it's too late.
Where would your favorite stretch of coastline be if the West Sheet melted? It wouldn't be. On NOVA's website, see for yourself what such a catastrophe could do. To order the show for $19.95, plus shipping and handling, call 1-800-255-9424. And to learn more about how science can solve the mysteries of our world, ask about our many other NOVA videos. Next time on NOVA, frightening power, lightning speed, and amazing drive for survival. Brave a close encounter. Crocodile. NOVA is a production of WGBH Boston.